Okay, so in this lab, what we're trying to do is we're trying to identify, for the 2 weeks that we're working, the rate law expression for the reaction of crystal violet with sodium hydroxide. So we have crystal violet reacting with hydroxide to give us this crystal violet hydroxide complex. Okay. Now when we're doing this, what we're trying to identify is the rate law expression. Okay, so it's going to be rate equals K, our rate constant, times the crystal violet concentration raised to some power, times the hydroxide concentration raised to some power. In last week's lab, what we did is we identified what the order of hydroxide was. And we did that by using the method of initial rates. Changed the amount or concentration of our hydroxide, measured the rate, and looked at how that rate was affected by the change in that concentration, all the while keeping our crystal violet concentration constant. In lab this week, we're not just going to do the same thing and change the variables and change concentrations of crystal violet, keep our hydroxide constant, and then look at it. There's another way that we can identify the order with respect to, in this case, crystal violet. We can do that by using integrated rate laws. Okay, so what we're going to do is we're going to collect data just like we did last week. So we're going to get a absorbance versus time curve. Okay. Now remember, our absorbance is proportional to our concentration. Okay, so if our absorbance cuts in half, our concentration cuts in half, specifically for what is being absorbed. Now remember, that's our crystal violet, right? That's the violet colored solution that gives us an absorbance here. Well, when we do that in lab last week, the reaction was really, really slow. So we didn't really see a big slope or curve. And this week, we're going to have a little bit higher concentration crystal violet, a little bit higher concentration of hydroxide. So that's going to make our reaction a little bit faster. Remember, the rate or reaction rate is proportional or is equal to our slope. So we're going to collect data, and it will maybe look something like this. Okay. There's different versions of what our data is going to look like. Now, if it looks like this, we want to identify, using our integrated rate laws, is it first order, second order, or possibly 0th order with regards to our crystal violet concentration? Well, the way that we do that is by looking at the integrated rate laws for a first order, 0 order, or second order reaction. Well, those integrated rate laws tell us something about what curve we may want to graph. Okay, so 0th order, when we go ahead and we are going to graph this, we're going to see that the concentration of, so I'm just going to use crystal violet now, at some time period is going to equal the concentration of our crystal violet initially minus our rate constant times time. Okay, so one thing to note here is that we have a constant decrease, right? There's a linear relationship. The concentration of our crystal violet doesn't affect our rate, right? That's the definition of a 0 order reaction. Okay, first order, we're going to see it has a little bit different of a relationship here. Okay, so we're going to see it's the natural log of the crystal violet concentration initially divided by our crystal violet concentration at some time is going to equal our rate constant times time. Okay, so now we have this relationship here, and we'll notice that it's not a linear relationship like it would be for 0th order, but our first order is a natural log relationship, and that has to do with how we would integrate these rate laws from our normal rate laws. Okay, then we also have second order. Okay, well, second order looks a little bit different. It's going to be 1 over our crystal violet concentration, and the sub T means at some time period after our reaction has started, is going to be equal to our rate constant times time plus 1 over our initial crystal violet concentration. Okay, so now we go ahead and we look at this, we see there's very distinctly different ways or relationships that we have for 0, first, or second order integrated rate laws. Now remember, our integrated rate laws relate 2 variables, concentration with time. So times are independent variable, concentrations are dependent variable. So we notice we can see that in all of these, right? Time, time, time related to our concentration. Okay, And so we can think about this, for example, our first one would be y equals mx plus, and this is our b here. Okay, we could rewrite it there. And so if we wanted to go ahead and graph something that would be linear, we want to see, can we graph something that would be linear for each of these different relationships? Okay, well, we could say this is y, so that would be our CV plus, would be our y-axis, equals, at some time, our negative kt, okay, so that would be m times x, right, because we want to get mx plus b, plus the concentration of our crystal violet initially, okay, and that would be our b value. So now if we were to graph our crystal violet concentration versus our x time, we should get a linear graph. So if we were to do time and crystal violet concentration, we're going to get something that's linear. Okay, so this would be, we collect our data, we graph those, and we get this linear curve. That tells us, okay, our reaction is zero order. Well, if we have our first order here, we see we're probably going to do something a little bit different. We don't have just this linear relationship. Okay, we see that we have this natural log relationship. Okay, well, if we're going to rearrange this, we would see that we would want to graph not just concentration, we would want to graph natural log of concentration versus time. Once we do that, we would also see that we get a linear relationship here. Okay. Now, if I were to graph natural log of crystal violet concentration versus time, and I did not get something linear, that would tell us it's not first order. Likewise, if I were to graph crystal violet concentration versus time like I have over here, and we can see this is definitely not linear, well, that would tell us it's definitely not zeroth order. Okay. And then we go back over here to our third relationship with the second order. Again, we can go back and we can see, well, if we want to graph something that would be linear, we could say, well, this is our y, 1 over crystal violet concentration. Our rate constant times time is our mx, and then our 1 over our crystal violet concentration would be b. So now if we wanted to graph this relationship, we're going to again want to graph it versus time. We'd see we want to graph 1 over the concentration of our crystal violet. And when we do this, we're going to notice that it is going to be a linear graph as well. Okay. Now note, these two have negative slopes, whereas our third one has a positive slope. Now the reason for that is because of the relationship between our rate constant and these curves here. So for this one here, going back to this here, we see our slope is equal to our rate constant. For this one here, we notice that, going back to here, our slope is equal to the negative of our rate constant. And our middle relationship here for first order, we would notice that our slope is also equal to our negative of our rate constant. So two things we can get from this. First, by graphing these different types of relationships, the one that is most linear will tell us whether or not crystal violet is zero, first, or second order in our reaction. Secondarily, we now are able to calculate our rate constant by just looking at our slope. By looking at the slope, now we have the ability to determine the rate constant value, which is important because now we're going to do this reaction at multiple temperatures. Well, once we do it at multiple temperatures, if we go back to what we've learned already, our rate constant changes with temperature. So now looking at these different temperatures, all we have to do is graph these relationships, and once we've determined maybe, okay, it's second order, I could go ahead and graph all the second order relationships, and then that's going to tell me all my rate constants for my 10 degrees Celsius reaction, 40 degrees Celsius reaction, etc. So hopefully this gives us a good idea of how we are going to accomplish the task of determining the order with respect to crystal violet this week, as we kind of look at these different relationships and these different graphs that we're going to do.